Another type of vector product. So we have the dot product or scalar product, and now we have the cross product. So we have two different kind of multiplications in vectors. And the difference between the cross product and the scalar product is a number, the cross product is another vector, and that vector is always perpendicular to the vectors that we started with. Here's our formula for the cross product. Very similar to the dot product. But in our cross product, we got the length of u, length of v times sine of theta. And then we have n as a unit vector perpendicular to the two vectors you started with. So we'll explain how we find out which way the vector is going, because we have to describe that in our answer. And we can figure it out by something called the right-hand rule. So this is writing it out and describing it all the way through. So what we're going to do, as you can see in this picture right here, oh, what a nice looking hand. If you have two vectors, u and v, you put your hand on the one vector so that you can bend your three fingers, except for your index finger, towards the other vector. So in this case, on the piece of paper, I've got my thumb pointed upwards. You could point in vector u by having your thumb pointed downwards. To figure out which way you need to point your thumb upwards, you need to be able to move your other three fingers towards the vector v. So in this case, if my thumb is upwards, I can bend my fingers towards v. If my thumb is down, it doesn't work. I can't bend my fingers back that way. So we would know if we did the cross product u cross product v, in this case, the resulting vector would be perpendicular and pointing upwards away from the paper. So we show that in the next picture here, where I've moved my three bottom fingers, my thumb is still pointing up, and we would have the cross product upwards. If we did v dot u, I would have to put my hand pointing down in order to move these three fingers towards u. If v cross u would be pointing downwards into the ground, perpendicular to the vectors you started with. Yes?
Have you ever had a student who had no right hand?
No right hand. So then, yes. Okay. If you happen to have no right hand, and you can't do the right-hand rule, the next way to think about it is to think about either having a wrench. Here we go. Here's u cross v. Okay? So our right-hand rule says it will be pointing upwards towards you guys, away from the screen, rather than inwards into the screen. Okay? But if you did not have a right hand for the right-hand rule, you could imagine having a bolt on that and having a beautiful wrench. There we go. If you took that wrench and moved it from u, oh, that's not the wrench. Let's see if I can. Okay, so the diagram is not doing but can you imagine I'm turning that from u to v? That wrench turns from u to v. What would happen to the bolt? Would it loosen or would it tighten? Loosen. And if it loosened, which way would it be heading? Out, away from the screen. If you tightened it, if you did v cross u, I actually like the wrench better than the right-hand rule, because especially when you're doing upside down, it just feels awkward. But if I move this wrench oh my goodness, this way, what would happen to that bolt? It would get tighter, screwing into the screen, or if it was on your paper, it would go down into the ground. So if you're tightening, then it's perpendicular into your paper. If you're loosening, it's upwards away. And I actually find that's easier than the right-hand rule. And if you've never, left hand also works in a different, yeah. Oh, well, Maybe not quite. And if you were like, but what happens if you've never seen a bolt or a wrench in your life and you don't have this experience of tightening or loosening, then just think about toothpaste. Almost everybody has had a toothpaste cap where they know which way it is to tighten and which way it is to loosen. And you can, same thing, if I go from V to U, if I turn this way, I'm going to tighten my...
My toothpaste cap is...
Oh, the flip top's such a
Wait,
problem.
What if, like, after, like, the vectors...
I still get my mom to put my toothpaste on my toothbrush.
what if, like, after the vectors has to see a giant hole where, like, someone tries to...
Maybe. Those are the risks I take in teaching this course. So that is the idea of this vector n. That vector n is either perpendicular going up or perpendicular going down. And it's a unit vector because the number in front is the magnitude of that vector. So the cross product, the values in front, give us the magnitude of the vector, and then we have to use the right-hand rule, a wrench, or a bit of toothpaste to figure out the direction, if it's outwards, away from the paper, or inwards. I once asked, is it because of vectors that they made screws and nuts and bolts do that? Did they do that on purpose? And the answer is no, because you could thread things either way. But when you're applying, because one of the applications of the cross product is applying torque, and you would want to apply torque in the direction that you're torquing. But no, it is not necessarily because of that, although it's kind of cool that it works that way. Okay? But U cross V then, as a result, is not equal to V cross U because they'll be going in opposite directions. They will be opposite vectors. They will still have the same length or same magnitude, but they will be going in opposite directions. Okay, so our first example. Okay, we have, if the angle between two vectors is 50 degrees, so this angle right here is 50 degrees, and the length of U is 10, and the length of V is 20. Obviously, this is not drawn to scale. Find the cross product U cross V and V cross U. So the cross product of U cross V, first of all, would be the length of U times the length of V sine 50 degrees times the unit vector n, and now we're going to have to describe which way n would go, okay, equals, and we know that the length of U is 10, the length of V is 20, sine of 50 we'd go to our calculator for, 0.766. And so we'd write our final answer, 153.2, where n and maybe you would say on yours, I mean, mine's on a screen, so mine is outwards away from the screen. Yeah, you'll find people while they're doing the cross product and trying to do the description doing something like I just did, either having their hand out and waving it funny, or I pretended I had a wrench and I was like taking apart a lawnmower.
So, like, do we have to, like, explain that it's out of the paper, or can you just use positives and negatives?
Well, you have to describe its direction. So I think upwards away from the paper or inwards through the paper would describe it. Yes? Yeah, it looks really terrible, doesn't it? Let's see what happens when someone else tries to understand it. Upwards. From. That's from. So my writing can't be that bad. Let's check this one out. Yeah.
Where A is a unit redshift.
Okay, this word apparently was supposed to be vector. Obviously, it was close. And this, I can understand the little hat on top of the N would be confusing for any computer because letters shouldn't wear hats, just like students shouldn't wear hats in school.
Is that from?
That's supposed to be from, yeah.
Is that a FM radio?
There we go. Perfect.
So, like, why shouldn't students wear hats?
Because unless they have a thinking cap, it's not helpful.
Or what if they are really cold? So, would you support, if, like, let's say this was a democracy, would you support repeal?
So, problem. Cross product applications. Here's our first one. Cross product and the area of a parallelogram. Do you know the area of a parallelogram formula normally?
B times
Right, here's your parallelogram. If this was your height and you took this part of your parallelogram and slid it over here, you'd make a rectangle. And the formula for a rectangle is just base times height. So the formula for a parallelogram is just base times height. So since that formula is really easy, we're going to introduce the cross product to do it in a more complicated way. Why not? Okay, so, oops, my picture is right here. And I think I probably should have done a graphical one of that. But if you have the cross product, U cross V, remember that U cross V is length of U times the length of V times sine of theta in the direction of n. If we look at particular certain things in this question, okay? Do you know in this right angle triangle here, let's draw it here. If I draw this right angle triangle again with this angle theta here and this as V and this as the height. Using SOHCAHTOA, would you agree that sine theta is opposite over hypotenuse? I should really label this is the length of that vector, right? Okay. Now, if I wanted to solve for the height, I could multiply both sides by the length of the vector v. And I'd get h by itself. So the length of u is the same as my base, and the length of v sine theta is the same as my height. And base times height is the area of a parallelogram. So whatever the coefficient or the number in front of your unit vector, in other words, whatever the length of the cross product is, will be equivalent to the area of that parallelogram. Which is kind of cool, really cool. Oh, and that's one we did already. I don't know why it switched back like that. Oh, it's because this one, there we go. All right, so there's the picture. So again, what I just described, you can solve for h. The area of a parallelogram is base times height, and this matches up with what's in the cross product. In other words, it's just the magnitude or the length of the cross product. So the area of a parallelogram can be found by just finding the length of the cross product. Okay. Ooh, fun. Sorry, I'm having fun. I'll calm down a little bit. Example 2. If the vectors in example 1 were made into a parallelogram, find the area of this parallelogram. I should go back to our first example. What did we find our first example's cross product to be? 153.2 times the unit vector n. Oh, we never did the opposite direction. We should have done that on this one, right? It'll be exactly the same in the negative direction. Since we've defined n to be upwards, by putting that negative, that changes its direction downwards. But you could, but if you went down, you'd have to introduce a new vector n because you are using n twice in the same question. So by defining n as a unit vector outwards, the correct answer should be inwards. But now that we've seen that our answer was 153.2 for this question, when we get this one, we know that U cross B was 153.2. The length of U cross V would just equal 153.2. So the area is 153.2 units squared, but we weren't given any units in this one to begin with. So the cross product is easy to find if you have the lengths and you have the angle in between them. If you don't have the angle in between them, there is still a way to find the cross product. So this is called the Cartesian form of the cross product because it uses the components. And it's a lot like the determinant of the matrices. Check it out. I'm going to take this fancy white box. There we go. For the first one, you hide the first column. And then if you took the remaining elements and sort of had a 2 by 2 matrix, can you see that the determinant would be A2, B3 minus B2, A3? Does that match up? For the second one, whoa, wait for it, no. Here we go. There it is. For the second one, if you hide those, what's the matrix? A1, B3 minus B1, A3, but it gets switched. Whew, whew. And then the third one, wow. There we go. Easy, there it is. It's back to A1, B2 minus A2, B1. So that formula can sometimes be difficult to remember unless you remember regular determinant, negative determinant, regular determinant, sort of as a connection to matrices. Or what we could do is sort of similar to the way that we found the determinant of a 3 by 3 matrix. We rewrite out the I, the j, and the k, the I, the j, and the k of the vectors. So A1, A2, A3, A1, A2, A3, B1, B2, B3, B1, B2, B3. And draw diagonals. The blue arrows are positive. The red arrows are negative. So if we look at I, if I just look at the arrow going through I, can you see that my positive ones are A2, B3. My negative ones through I are A3, B2. If I look at what's going through K, if going through K, the positive one is A1, B2. No, A1, wait a minute. IJ. I'm going alphabetically wrong. What's after I is J. If I go through J, I've got A3, B1, and my negative one through J, A1, B3. And then if I go through K, I've got my positive one, A1, B2, and my negative one through K, A2, B1. Not sure if this is easier or not. So consider the vectors u and v. Find the cross product u cross v. Since we don't know the angle between them, we'll use the Cartesian formula. So you can either do I, j, k, I, j, k. First vector, 2, -1, 5, 2, -1, 5. Second vector, -6, 3, 8, -6, 3, 8. So u cross v will equal, for my I component, I will need to have through I diagonal this way. That would be my positive one, ends up being -8. Subtract my diagonal this way, 15. Wow. For my vector j, I need a positive one, which ends up being -30. Subtract, in this direction, 16. And for vector k, positive direction is 6. Negative direction is also 6. Simplifying this, -23, -46, 0. We don't have to say the direction it's going because the vector answer that we got has a direction. But the answer that we got, -23, 46, 0, is perpendicular with both u and v, which is fascinating. Check it out. What happens when you do the dot product of the answer with u? What should we get? 0. And the dot product with the answer with v, we also get 0. So we can check with the dot product to see if they're perpendicular. In this case it is. And we just, using the cross product, found a vector quite quickly that is perpendicular to both of those vectors. That's whoa. Okay. Consider the vectors u and v. The cross product is w. Find x.
X is 2.
X is 2.
Yes.
It's easy. No problem. Well, we could go about this in a couple of different ways. You could use your dot product, right? Because what do you know? You know that v dot w has to equal 0. And if I did the dot product, I would get 6 minus 44 plus 19x has to equal 0. 19x equals 38. Divide both sides. X is equal to 2. Is that what you did?
That's not what I did.
Okay. What did you do to find out x is 2?
I used the, like this, or like through that, and then from that.
So you used the cross product formula
Yeah.
to work through here. So example, using the cross product formula, the I component would have to equal 3x minus 4. And that having to equal 2 tells me that x has to be 2. I find when I'm just looking at vectors this way, I actually find the determinant method a little bit easier for finding the cross product. So to find that 3x minus 4, I ignored my first column and then just the determinant of what's left, 3x minus 4. That's not actually the determinant, but I say that because it's so much like what we did in matrices. The only time is when you move to this one, you have to do the negative of it. Okay. Example 5. Consider these vectors. This is one for you to try. I want you to find the area of the parallelogram, which now this is pretty amazing because you have to think in 3 dimensions. So sure, you could do base times height, but the math you'd have to do in 3 dimensions to try and draw this out for yourself. Or you could just use a cross product. And then I want you to find the angle between those vectors. First of all, the area of the parallelogram can be found with the cross product and the length of, so the area is going to be the length of the cross product. So we have 2 different formulas for the cross product. We could either use the Cartesian form to get the vector that's the cross product, or we could use the length of u, length of v, sine of theta, but we would need to know the angle. The way that this question is worded, that says find the area first, so then I'm going to use the Cartesian form. So we're going to say that u cross v would equal -3 minus 4, and then 6 minus 36, and -6 minus 27. So I'm using the Cartesian form. I was using the discriminant method in my head. Did anybody draw out the arrows? Okay. And just double checking, because I did it rather quick there, did you get -7, 30, -33? That's our cross product. So if we want to find the area, our area is the length of our cross product, which is a squared, 49, plus b squared, 900, plus c squared. Oh, mental math's not working for that one too quickly today. 33 squared. I feel like I should know that quicker. 1089. Oh, it's a pretty number. So we get the square root of 2038 45.144 units squared. So whatever your scale was for your vectors, like if you were using grid paper that was 1 centimeter by 1 centimeter, then that area would be 45.1 centimeters squared. Find the angle between these two vectors. Now we have some options. We could use the dot product formula. We know that, or we could use the cross product formula. Okay? Our dot product formula says that cos of theta is u dot v over length of u, length of v. The dot product of these two would be negative 54 plus 3 minus 4. The length of u is 36 plus 9 plus 16, square root of 61. And the length of b, 81 plus 1 plus 1, square root of 83. I prefer using the dot product opposed to the cross product, because with the cross product, you're solving for sine. And with sine, the cast rule tells you it's positive in quadrant 1 or in quadrant 2. So using that, you will not be able to easily determine, should I use the acute angle or should I use the obtuse angle? But using the dot product with cos, I can see right here that I have negative 55 over the square root of 61 times 83. I know that my answer is going to be the obtuse angle because of that. So I go to my calculator, I do cos inverse of negative 55 divided by the square root and we get that theta is 140.62 degrees. So a little analysis of our cross product. List of properties. If you do the cross product in the other order, it has the same magnitude but opposite direction, and so it will be the negative. Thinking about how complicated the cross product is, you might wonder why you would ever want to do more cross products, but you could. But in this case, I would highly recommend adding the vectors first instead of doing extra cross products. But if the cross product can be distributed, you could also factor out the cross product and add first to make life easier. Okay, and the distribution can happen in either ways, whether you're adding first or adding second. If the cross product is 0, and both u and v are not the 0 vector, then your vectors are parallel. So now we have another way of showing two vectors are parallel by using the cross product. However, I would still recommend using our previous method of showing two vectors are parallel by showing one is a multiple of the other one. You know how we set up both of them equal with a k in front? I would still use that to show parallel, easier than using the cross product. Now in mathematics, 4 and 5 might feel to you that I've said the same thing. But in mathematics, it's not always true that if something works one way, working backwards, it still works. But in this case, it does. If the cross product's 0, then they're parallel. If they're parallel, then the cross product is 0. It works in both directions. And if you have a scalar multiplied by a cross product, you could put that scalar in at the end, or you could put it in early. That's the last property. We have one more application of the cross product that we're going to do. Or did I? Oh, sorry, I missed example 6. We have example 6, and then one more application of the cross product. So here we have these vectors. Use the cross product to show that they're parallel. So the cross product of A and B, -4 minus a -4. Second one would be 6 minus 6. And then finally, 12 minus 12. Since the cross product is the 0 vector, A and B are parallel. Again, the more typical way of showing parallel would say, does there exist a K so that these are equal? And the answer is yes, if K is equal to -2. If the dot product's 0, then they're perpendicular.
Right. So if it's
Not necessarily, because you could have values for the lengths that multiply with the cos that could still give you 1. All right. So the last application of the cross product in physics is torque. So those of you that have taken physics, you might have had a torque formula that you used. Torque is the measure of force on an object which causes it to turn. So this is sort of like our wrench on the bolt idea. Okay? We've got two vectors. Our torque vector is equal to the arm, in other words, our wrench, and then the force pushing on that arm with the angle theta representing the angle between the two vectors. Units for torque are Newton meters. So let's look at a consideration here. We have a wrench 15 centimeters long used to tighten a bolt. A force of 50 newtons is applied to the bench at an angle of 85 degrees in a clockwise direction. So we got to draw a picture. Here's our bolt. Right? Nice and perfect. And we've got a wrench 15 centimeters long. We're tightening it. So if you think we're going in clockwise direction. Here, look at this beautiful wrench drawing. Maybe I'll take the drawing away. It's bad. My earlier wrench was much better. It's more.
that one honestly I think it's better.
Okay? So there's our wrench. It is 15 centimeters long. So we can call this, the length of A is 15. A force of 15 newtons is applied to the wrench at an angle of 85 degrees. At an angle here of 85 degrees. I guess if you're applying the force at 85, the 85 would actually be here. Is that right? Does that make more sense? You're applying the force this way. 85 degrees right there.
I mean, pushing it from up there,
Same idea. Right. It's just when we put this together, so we have our arm vector here, when we want to figure out the cross product, what is the torque on this, we're going to take this 50 newtons, we're going to move it there, our 85 degrees moves there. Now our vectors aren't on top of each other, but we're looking at what's happening to this bolt, because the result is going to be, right, in this direction, it's going to loosen, no, it's going to tighten, so it's going to go in towards the screen when we tighten it. And we can find that amount of torque by just doing the cross product. So what is our cross product here? So our torque is A cross F, which is the length of A, or the magnitude of A, the magnitude of F, sine of the angle between them, which is 85 degrees. We're already told that the length of the wrench was 15 centimeters, which, since the units are Newton meters, I'm going to change it to meters, 0.15. We know that our force is 50 newtons, and we can figure out sine of 85 on our calculator. It's less than 1. Oh. Can you see why a 90-degree pressing on that wrench would be a better idea? Have you ever tried tightening a bolt by pressing just straight on the wrench as hard as you can? It's not very successful. Even if you try just 1 degree difference, you're not going to have very much torque. So you have the greatest torque you can start to see from the formula. Makes sense when you're pushing right at 90 degrees. And multiply all of these values together. Oh, and we have to include the n. We get 7.47 n. And again, we need to describe for you guys, it'll be into your page tightening that bolt.
Could we like just get rid of the and then just say into the page?
Well, we have to, no, you have to have that n vector, that it's a unit vector.
Well, universe is just
Right, and then so the 7.47 is
so if we say
the length of that vector going into the page.
7.7 millimeters into the page, that would be the same thing.
Right. Yes, in this case it would be. Because the length of That vector is 7.47. So the torque is 7.47 Newton meters. Okay? So you can see where, you've probably learned this from physics or science, where you have the longer the wrench, what that increases the torque on your bolt, which helps you hopefully tighten it or loosen it. So when my car got a flat tire and I went to the trunk and pulled out the wrench that they had provided for me, and it was like this long, just about a foot long, and I was like jumping with all my weight trying to loosen the bolt so that I could change the tire. I looked in my garage to see if I could find a pipe to go on top of that, because I knew if I had a long pipe it would just be like easy. But no, there I was with my entire weight jumping on this little wrench, the imprint of which was left on my hand for a good 5 minutes. But I eventually changed the tire and everything.
300,000 meter long wrench. There would be a lot of torque there.
Yes. So what we can say is, in part B, we already found the magnitude and direction of the torque vector. But in part B, what angle should be applied? Because we want sine of theta to be 1, as big as possible, we would need that angle to be 90 degrees.